Hello friends, welcome back to Online Math. We have this interesting equation right here to solve. Have you ever wondered what is actually going to be the solution to this simple and of course interesting equation? And well, you may think it doesn't have any solution, but just need to follow through and then see how we are going to find a solution that will satisfy this problem we have right here on the screen. Okay, so let's delve into this video. So of course, whenever you have an unknown as the exponent, one of the most natural thing to do will just be to take the natural log of both sides. Okay, so if I do that, I'm going to be having the natural log of 1 power x, okay, is equal to the natural log of -2. Okay, then of course at this point I am gonna actually apply the natural log property. So I'll bring down this x right here. So I'm gonna be having x multiplied by the natural log of 1, okay, is equal to the natural log of -2. Okay, so of course this is one of the most basic way to solve this, but then you wouldn't go further and then you discover that there's really a problem, because of course natural log of 1 here is 0, and then 0 times x will give you 0, but then 0 is not equal to the natural log of -2, and of course natural log of -2 does not also exist in real numbers. Okay, so how are we going to go about solving this problem? So what we're going to do next is just to find a way to extend our solution to this problem to complex numbers. And so we want to find out some complex representation of some of these numbers, and then we can begin to simplify further there. So if you remember the polar exponential equation, which is exponential I theta, which is defined as cos theta plus I sine theta. Okay, so if you can remember these, this is also called the Euler formula. If we decide to substitute theta for 0, you're actually going to be seeing that exponential. So if I put 0 here, if I put 0 for theta here, 0 times I will be equal to I. So I have exponential 0 is equal to cos 0 plus I sine 0. Okay, and of course sine 0 is equal to 0. 0 times I remains 0. So this part turns to 0. And then cos 0 is equal to 1. So you see that exponential 0 is equal to 1. Okay, of course you can also want to check out the value, what the value of this exponential equation will be when theta is equal to 2 pi, and of course you're actually going to be discovering that it will still give you equal to 1. So we have exponential I 2 pi is equal to cos 2 pi, okay, plus I sine 2 pi. Okay, so this is what we have, and then sine 2 pi is equal to 0. So the whole of this part turns to 0, and then cos 2 pi is also equal to 1. So you see that exponential I 2 pi is equal to 1. Okay, so of course in general you're actually going to find out that whenever theta is equal to 2 pi k for all integer values of k, this exponential equation is actually going to be giving you equal to 1. Okay, so exponential I 2 pi k is equal to 1, and of course this is going to happen for all integer values of k. So what we're just going to be doing is, instead of this one in our equation, we're going to represent it, of course we're going to replace it with exponential I 2 pi k. Okay, so that we're going to be having in this place where we have natural log of 1 power x is equal to the natural log of -2. I'm actually going to replace this one here so that I have natural log of exponential I 2 pi k. Okay, and then of course I'm going to use this x to also multiply this power, so I have x right here is equal to the natural log of -2. Okay, so applying the property of natural log, I'm going to actually bring down these powers right here. So I have I 2 pi k, okay, natural log of exponent is equal to the natural log of -2. Okay, and of course at this point you see that natural log of exponent is equal to 1. So obviously what I'm going to have in here is I 2 pi k is equal to the natural log of negative 2. Okay, sorry, there is x here, don't miss that. And then because we are looking for x, we can just go ahead to divide through by the coefficient of x, which is I 2 pi k. Okay, I 2 pi k, okay, is equal to the natural log of negative 2 divided by I 2 pi k. Okay, so that this is actually going to cancel this, and then we have our x to be equal to the natural log of negative 2 and then divided by I 2 pi k. Okay, but of course I is not actually going to be on this denominator, so we're actually going to multiply both the numerator by I and also the denominator by I, so that we can remove this I here at the denominator. Okay, so that what I'm going to be having is that I multiplied by the natural log of negative 2 divided by, okay, 2 pi k. Okay, and of course I multiplied by I is equal to negative 1, so I'm going to bring up the negative 1 right here. So this is what we have at this point as the value of x, but then there is still more problems which we need to simplify, because this natural log of negative 2 does not exist for real numbers. So we want to also find a way to simplify this and then have some complex expressions for it. Okay, and of course you know that we can write this natural log of negative 2 as natural log of negative 1 multiplied by 2. Okay, so that at this point I am actually going to apply the rule of natural log, where if you have a multiplication you can expand it by summing the terms. So I have the natural log of negative 1, okay, plus the natural log of 2. Okay, so you can see we have this is actually going to give you a real number, but then this does not exist. Okay, so in order for us to get an expression for negative 1, we just need to consider the polar exponential equation we looked at earlier on, which is exponential I theta, which we define as cos theta plus I sine theta. Okay, and then you notice that when we substitute theta to be equal to pi, this exponential equation is actually going to change to negative 1. Okay, so we're going to be having cos pi plus I sine pi. Okay, so this is what we have at this point, and then of course you're actually going to be seeing that exponential I pi will be equal to, this is equal to minus 1. Okay, and of course this part is also equal to 0. And then of course in general you're actually going to be noticing that for theta equal to pi plus 2 pi m, that is for all integer values of m, this exponential equation is also going to be giving you negative 1. Why? Because cos pi is also going to be giving you the same as cos pi plus 2 pi m, and of course this is actually going to be true for all integer values of m. So in general we're actually going to be replacing this negative 1 with exponential pi plus 2 pi m. Okay, so this is also exponential I multiplied by pi plus 2 pi m. Okay, and of course we just see that this is gonna give you equal to negative 1. Okay, so in place of this stuff we have right here this negative 1, we're actually going to be replacing that with this exponential equation, so that the natural log of negative 2 now becomes the natural log of exponential I into pi plus 2 pi m. Okay, and then of course plus the natural log of 2. Okay, so simplifying further, what I'm going to be having is I pi plus 2 pi m, okay, multiplied by the natural log of exponent, and then of course plus the natural log of 2. Okay, so this is equal to 1, and then this stuff we have right here is now I pi. Okay, don't forget this is also in bracket, so if I multiply 2, I'm going to be having I pi plus 2 pi mi, okay, and then of course plus the natural log of 2. So I'm actually going to replace natural log of negative 2 with this expression we have over here, okay, so that our x is actually going to turn to, okay, so x, which we got as I natural log of negative 2 divided by 2 pi k, okay, so this is actually going to change to I into I pi plus 2 pi mi, okay, and then of course plus natural log of 2, okay, so this is what we have divided by 2 pi k. Okay, so but then of course remember we had a negative right here, so this is also negative I, so I'm going to factorize this I pi that is common right here, okay, so that I'm going to be having negative I into I pi, okay, and then multiply by 1 plus 2 m, okay, and then of course plus the natural log of 2, and all divided by 2 pi k, okay, so that if I use this now to multiply this, my solution is actually going to be equal to, and this I multiply this, I'm going to be having minus 1, and then of course minus 1 times minus here is plus, so that I have a pi into 1 plus 2m, okay, and then of course when this minus I multiplies natural log of 2, I'm going to be having negative I natural log of 2 divided by 2 pi k, okay, so this is actually going to be true for all integer values of k, okay, and then of course integer values of m, and of course our k is not equal to 0 because of this. If k becomes 0 here, there is a problem, okay, so this is actually going to be the value of x which will satisfy the problem we are solving, okay, but of course this is not a general solution because you can see that all of these conditions must have to be met before x will be a solution to the equation we are solving. So x must have to be an integer and m will also be an integer, and then of course when these conditions are not being met, we wouldn't know what is gonna be the value of x, so we don't know whether it is actually going to satisfy that. Okay, so that is how you actually solve this, and then let me have your thoughts in the comment section, and subscribe to our channel, like this video, and I'm going to see you guys in my next video. Bye.